We're going to start talking about exponential functions. So exponential functions look like this. It's some number times some other number raised to the x power. So now the x is the exponent, and that's why it's called an exponential function. What we've done before were called power functions because the power was x raised to a power. And I've already misspelled the word. Exponential functions. So b is your base. We're going to call this the growth rate. Although sometimes it's actually a decay rate if that number has a certain value. But it's how much it's growing by. Now, it's very, very important we understand order of operations when we do these problems. We do not ever multiply a times b first and then raise it to the x power. As you know, that you always have to do exponents first. So the multiplying by a is always the last step. Whenever you're like plugging values in for x, you always want to raise b to the x power, get that number, and then multiply by a. That's probably the biggest mistake I see happen over and over again. So let's try to not make that mistake. We'll talk about that mistake right away so that way it does not happen. Does that make sense? That b goes to the x power, whatever number that is, raise it to that power, get that answer, and then multiply it by a. The value of a does have some effect on the graph. Okay, it can speed up the growth. It can also slow it down depending on the value of that number. And just like all of the other things we've graphed, if it's negative, it can reflect it, right? Reflected over the x-axis. So that a value actually has the same effect that it had on your parabolas, on your square root functions, cube root functions. That value of a is pretty consistent throughout all of the different functions that we've done so far. Okay, make sense? A little bit so far. We just haven't taken a look at any numbers yet. So that b value. So if I would say that the b value is a 1, if b is 1, then that means it always stays the same. So in all of these problems, the b value will never actually be 1 because that means it's not actually growing at all. So if you think about it, if we would make a table, if you can imagine the b value was 1, so let's say a was 1 because that we'll just say the a value was 1 and the b value is 1. If we take 1 to the x power and I put a bunch of different values in for x and made a table, what would always be the output, the y value? Think about it. No matter what value you put in for x, what will always be the output? 1. That would be a really boring graph, wouldn't it? It would show no growth. If you were running a company and you just had a graph that looked like this over time, you'd be like, we're not making any money, right? That's pretty boring. And you're like, well, at least we're not losing money, right? We're just staying pretty constant, right? We're still in business, but we're not really growing. We're not losing, but we're not growing either. So in our problems, we're not going to do any problems where the b value is 1 because it's not very exciting. Okay. So in our problems, b value is either going to be bigger than 1 or it's going to be smaller than 1. However, it will never be negative. Let's write that down. B is never negative. That's important. It will make more sense tomorrow when we start applying it to word problems, and we really explore what that growth rate is. And when it comes to context and doing word problems, it will make total sense why the b value can never ever be negative. So just hold on to that thought for today while we graph, and then tomorrow when we apply it to some actual problems, we'd be like, oh, that makes total sense why b can never be negative. All right, so if it's bigger than 1, b is greater than 1, then what we have here is a growing situation. That's going to be a growth function. And those growth functions always look the same. They always have the same general shape. That's what they look like. They always cross the y-axis somewhere pretty low, maybe here, and then they grow like crazy. Woo! They take off. And then to the left side, they get smaller and smaller and smaller and smaller and smaller. They get closer and closer and closer, but they never actually touch the x-axis or cross over the x-axis. What does that make the x-axis? What do we call that when it gets closer and closer and closer to something but never actually touching it? An asymptote. Very nice. Thank you. Glad you remembered that. Let's see if we remember how to spell it. Remember that silent P in there? So we have the situation where there's an asymptote. There's like a boundary line. It gets closer and closer to it, will never ever cross. So this is what we would call a positive growth function. It's positive because it is above the x-axis. This is positive growth. If you look at it from left to right, as x is approaching infinity, right, as x is getting bigger and bigger, what's happening to the y values? They're getting farther and farther away from the x-axis, right? See how it's getting farther and farther away from the x-axis? It's a positive growth. Now, if there's positive growth, what else do you think there might be? Say it? Yeah, there's probably going to be a negative growth, and you're exactly right. And where do you think negative growth would live? Just use some common sense here. Where do you think? Under the x-axis, right. Right. So a negative growth function looks like this. You still have, as x is approaching infinity, we still have the y values getting farther and farther away from the x-axis. It's just that they're moving in a negative direction away from the x-axis. But these are both growth functions. So what would make the difference is the a value. With a positive growth function, the a values are always positive. A is positive. And with the negative growth function, the a is going to be negative. It's simply a reflection over the x-axis, right? That's what a does, right? When a is negative, it reflects it over the x-axis. So I want to make sure we get our head around the fact that we could have growth functions that are both positive and negative. Questions there about how we could have a growth function that seemingly looks like it's going down. The purple one there, even though it's going down, it's still a growth function because it's moving away from the x-axis. It's getting bigger and bigger because it's getting away, moving further and further away. It's about the distance away from the x-axis. That's what's making it growth. All right? Now, we still haven't even put any numbers in yet. We still haven't graphed anything yet, right? So let's do that now. But both of these are growth functions. Okay, let's try one with some numbers. So let's try to graph, and we're gonna pick a couple points. Let's graph f of x is equal to, let's do 3 times 2 to the x. And we're going to make a table. And we're going to pick a couple of points. And the 2 points I would always recommend when you're dealing with a growth function is to use 0 and 1. Those would always be the 2 points I would say to pick. Those are your key points. Choosing 0 for your x would give you your y-intercept, right? Plus, putting a 0 in for x makes life easy because anything to the 0 power is what value? Anything to the 0 power is? Anything to the 0 power is? 1, right? Remember, we could take Eiffel Tower and take it to the 0 power, and the answer is 1. We had a couple questions like that on the last test. Remember, I had the crazy thing in parentheses, like all kinds of stuff inside, and I raised it to the 0 power, and the answer is just 1. Doesn't matter what is in the inside, right? If you raise it to the 0 power, the answer is 1. So that's why it's nice to always use 0 as an exponent, because it doesn't matter what that base value is, right? That makes that easy. So I'm putting that in place of x. So 3 times 2 to the 0 power. And I want to know what the output is. Well, we've already figured out that that means the same thing as 3 times 1, which is obviously, isn't that 1? I mean 3, sorry. Screwed that one up. All right, so that's the point 0, 3. So we plot that point. And 1's also easy because anything to the 1 power is itself. So 3 times 2 to the 1 power, that would be 3 times 2, which is equal to 6. So then I plot the point 1, 6. I have these 2 points, and they then give me my shape that I'm going to have for my exponential curve. Now remember, I have that asymptote, right? My asymptote's the x-axis. See, I could put a really, really huge negative number in. Would it ever make my output become negative? Do negative exponents ever make anything negative? No. So like if I put negative 10 in for x, everybody put that in your calculator real quick. Put a negative 10 in for x. Do 2 to the negative 10 power, and then multiply it by 3. You should get some very, very small positive decimal number, right? That's the whole idea. You get something really, really small. You can barely even graph it, right? But that's an asymptote. So you're going to graph it like this. It's going to go through those 2 points, and it's going to go up like crazy, right? There's your graph. It's a growth pattern. As you get x and x gets bigger, as x approaches infinity, the y value gets further and further away from the x-axis. So that's why we've been saying for so long, negative exponents do not make anything negative. There's no value of x you could put in that would ever make your output ever cross over that x-axis into negative land.